Eugene Lytvynov. This is a joint talk with Dmitry Finkelstein. Dmitry Finkelstein is he was studied in our Institute of Mathematics, so we know him. Many of us know him very well. And Maria Oliveira. And the title of the talk is List Structures of the Sheffer Group over Hilbert space. Please begin.
Okay, so thank you very much. I would like to thank first the organizers for the opportunity to give a talk at this conference. So I'll be speaking about the so-called Sheffer group. And what is first the Sheffer group? So Sheffer here means relation to Sheffer sequences of polynomials. Okay, and the theory that deals with Sheffer sequences is called umbral calculus. So umbra is in Latin shadow, and what happened for many years is that mathematicians dealt with certain polynomial sequences at a completely formal level. So there was no idea why their calculations work, but nevertheless, for many polynomial sequences, they produced correct results. And actually, the explanation of why this calculus made mathematical sense was given by Giancarlo Rota and Stephen Roman in the early 1970s. Okay, and this theory nowadays is called modern umbral calculus. Okay, and so it studies various properties of Sheffer sequences, and I would like to say that also among all Sheffer sequences, there are two very important subsets, and these are sets of binomial sequences and other sequences. And there are various topics that are studied there, but one of the essential objects, and some say even the most interesting point of umbral calculus is the so-called umbral composition. So umbral composition is in fact just a usual product of linear operators if you define these operators through polynomial sequences. So this was known for quite many years, and then first completely independently, algebraists studied the so-called Riordan groups. So these are groups of infinite triangular matrices. And then it was discovered that actually these two objects are isomorphic. Then I would like to give a reference to this paper by 5 authors published in Advances in Mathematics of 2017, where the authors gave a description of Sheffer groups of polynomials are in the real line as an infinite dimensional Lie group. So even when you start with a real line, the group is infinite dimensional. And the reason is that if you go, for example, to the isomorphic Riordan group, so it is represented by infinite matrices. And actually, before that paper, there was also one preprint by Bashir, which was published just as archive preprint, and by some mysterious reason, it was not published as a paper. And already that preprint contains some important ideas that somehow the main result that was in this paper was a representation of discussion of the Sheffer group from the point of view of Milnor's theory of infinite dimensional Lie algebras. And also, I would like to mention that if we take just the binomial group, then it is isomorphic to the so-called group of formal power series, where the operation is substitution or composition, if you wish. And again, a lot of research was done there, and I can mention here this review paper by Babenka, where he discusses various topics related to this group, in particular, various geometric topics. Now, what I said before was related to the real line. You can go to a multivariate case, and this was done already in the early 1970s. However, all these studies of the finite dimensional case had the drawback that they were basis dependent. And then somehow the aim was to create umbral calculus, which would be basis independent, and where there were some efforts to do this, but somehow we realized this idea completely in our joint paper with Dmitry Finkelstein, Yuri Kondratyev, and Maria João Oliveira, and JFA 2019 paper. Okay, so what I'll do now, I will explain what is a Sheffer polynomial sequence and or infinite dimensional space. And as an example of an infinite dimensional space, I will take a Hilbert space. So actually the theory can be also discussed on other infinite dimensional spaces, but then this will probably require more difficult apparatus. But already at the level of the Hilbert space, one can see all the main points which appear in this approach. So I will use for my purpose the so-called standard triple of Hilbert spaces, which is very well known in the department of functional analysis. And for those of you who may be not that familiar, so we have central space H naught. So we have a space, Hilbert space H plus, which is embedded into H naught, and then H minus is the dual of H naught with respect of H plus with respect to H naught. So if you don't know this theory, just think of H plus as a Hilbert space and H minus is its dual. And if you want to be completely trivial, so to say, just think of just a single Hilbert space where you realize the dual space with this, by using the inner product in the Hilbert space. Okay, so then we go to the, when we take tensor power of this Hilbert space, okay? And in all this talk, I will be using the so-called symmetric tensor product. So symmetric tensor product of a Hilbert space is a Hilbert space. Again, if you're not familiar with the symmetric tensor product of Hilbert spaces, just think of L2 space over a real line, for example. Then its nth tensor power will be L2 on Rn. And then symmetric tensor power will be the subspace of L2 Rn, where the functions are symmetric. Okay, so this will be our starting object. And then we will denote by the brackets, by angle brackets, the dual pairing between elements of, well, this actually should be H minus. Yeah? So between the elements of the negative space and positive space. Now, what is a polynomial on H minus? Here, the definition is quite standard. What you do, you define a function P. So this is a function. So our function will be on the negative Hilbert space on H minus, and it has this form. So I take sum over K from 0 to n. I take the K's tensor power of omega. Omega is my variable, and I take the pairing of it with a positive element Fk from the positive space. Okay, so this is a nice space of functions, and this is a vector space, and one calls it the vector space of polynomials on H minus. And it is very easy to introduce topology on this space. You just identify this polynomial with these functions Fk, and you put on these functions they're coming from the Hilbert space, and then you take the direct sum of these Hilbert spaces, which gives you a topology on the space of polynomial. So this is easy. Maybe not less straightforward question is, what is a polynomial sequence on H minus? There is no way that one can deal here in the way that is standard in the finite dimensional calculus. Instead, what one needs to do is to look at maps. So we take space of all linear transformations of the space of polynomials, and we take those transformations, those linear maps, which map any monomial of degree n into a polynomial of degree up to n. Okay, and we'll say that this is a polynomial sequence on H minus, and we will also look in this talk in the so-called monic polynomial sequence. So monic in the classical setting means that the leading coefficient is 1. So here we assume that the Pn operators, so Pn operators, yeah, so they map Fn from the space, from the S tensor power to HK's tensor power, yeah, so that this dual pairing has meaning. And P and N is identical. So this is why we call this model. Obviously,
may I ask you, what
yeah,
is
sure, of course.
the last identity P and N is 1. This means that in some sense we have a monic polynomial, and this map is we just add summands of less dimension on something.
Yes, summands of less power. Exactly.
Less power.
Summands of less power. Exactly. And So if you think you can choose monomials as a basis, and then you have P representation of P as a matrix. Okay, so I will take P as a matrix PKN. So PKN maps H plus 2 power n to H plus 2 power k. And obviously PKN we set to be equal 0 for k larger than n. Then this matrix P is upper triangular. Of course, this is block matrix because each element of this matrix is an operator. Okay, and on the diagonal, we have identity operation. Okay? So this is one way of thinking about polynomial sequence. Another way is by going to the dual operator. So if I take the adjoint operator, PKN adjoint, yeah, so this is now operator from the k's tensor power to the n's tensor power, right? Then I can write the image of this monomial as Pn of omega Fn, where Pn of omega is now written in this form, yeah, so which now probably more resembles the classical form of a polynomial. So each Pkn maps. So this is an element of the k's tensor power, and you map it to the element of the k's tensor power. And of course, the P and N operator is still 1, right? Because the adjoint of identity is identity. And somehow in this talk, I will use either the language of linear transformation or the language of P and omega somehow without caring about it. It's the same object for me. If you wish, you have a linear transformation, and this P and omega gives you a representation in a fixed basis of your linear transformation. Okay. Now, a Sheffer sequence is then a monic polynomial sequence which has this form of the exponential generating function. So Xi is an element of the positive space, omega is variable. Okay, so I take summation of all polynomials C to power n 1 over n factorial, and there are elements on the right hand side. The first one is the exponential function. So it's exponent of dual pairing of omega with b of Xi and times a of Xi. Now, what is b of Xi? B of Xi has this form. Okay, so it starts with Xi plus higher order terms, where you map them Xi to power k, you map by a continuous linear operator into H plus. And the B1, as we said, is identity operator. And AK, this is, if you wish, this is a function with values in R, so it acts or like this. Yeah, so again, A naught is 1, and then you look at the k's tensor power of Xi, and you map it by using a continuous linear transformation into R. Now, of course, generally speaking, all these formulas have no meaning because nobody said that B is series conversion. Therefore, one needs to understand these formulas as it is done in combinatorics, which means at the equality of formal power tensor series. Okay, just replace Xi by T times C, where T is a variable, is a real variable now. Just expand everything according to the standard formula and equate the coefficients. So this is how people do it in combinatorics. Okay, so this is the definition of a Sheffer sequence, Now, there are two subclasses in the class of Sheffer sequences. One is the upper sequence. So for upper sequence, this transformation is Xi. B of Xi is Xi. Okay, so this is therefore this form of the generating function. And the other subclass, and we denote this subclass by blackboard A, and the other subclass, which we denote by blackboard B, is the subclass of binomial sequences. And the binomial sequences are those for which A of Xi is 1. So now we have the generating function, right, which is completely determined by the function B. And why we call these binomial sequences? Because we have this analog of binomial formula. So if I take Sn at sum of some omega plus zeta, so I have this decomposition. Well, of course, instead of multiplication, I have to use the symmetric tensor product. Now, what is the umbral composition? This is straightforward as soon as you're thinking of polynomial sequences as linear operators. So you just take the usual product of two linear operators. So this product of two linear operators gives you a new linear operator, and this new linear operator identifies a new monic polynomial sequence, right? And you call this monic tensor, and this call this umbral product of two polynomial sequences. And if you think in terms of matrices, infinite matrices, then this umbral product is nothing else but just the product of two matrices. Okay? And one can, for example, very easily see that if you take all monic polynomial sequences, then this is trivially a group. Now, what we are interested in is actually the Sheffer subset. And the statement is that actually this Sheffer set is a group under umbral composition of monic polynomial sequences. Okay? So this is one statement. And the second statement is actually both A, the upper sequences, and B, the binomial sequences form subgroups of S. And actually one can even show more that A is a commutative normal subgroup of S, and actually S is the semi-direct product of A and B. Okay, so this is a statement. And actually one can explicitly describe what happens to the umbral product of two Sheffer sequences. So for this, let's take two Sheffer sequences, and they have their generating functions. So I have functions A1, B1, and A2, B2. Then the statement is that if I take S, the umbral product of S1 and S2, then this will be a Sheffer sequence, right? So it will have its function B and A. And what is B? B is just the composition of B1 and B2. So composition or substitution, if you wish, right? And A is obtained in this way. So you almost multiply A1 by A2, but of course this is not just, it's a semi-direct product. So what you actually do, you take composition of A1 with B2 and you multiply it by A2. So this is the full description of this umbral product in the Sheffer group. Now we want to understand this as an infinite Lie group. So, and in order to achieve this, we will first look at the trivial situation. We will first look at the group of all monic polynomial sequences, and we will see that this is obviously an infinite dimensional Lie group in the sense of Hilbert. So we take as a vector space V all linear transformations V, right, given by these matrices, which are a triangle, but now on the diagonal, we have 0. Okay? So essentially what happens, we take monic polynomial sequence and we subtract identity operator from it. Now, the space, such a space, can be obviously endowed with a product topology of the corresponding spaces. So I have here Hilbert spaces, the space of linear operators from one Hilbert space to another Hilbert space. It's a Banach space, and now I take this infinite product of these Banach spaces. And this makes this the complete locally convex topological vector space. And then, as I said before, I have this trivial bijective map between the space of all monic polynomial sequences and the space V by subtracting identity from the monic polynomial sequence. Yeah? Subtracting identity from the map. And this gives immediately a topology on M, right? Because I have a topological vector space, I have this bijection. And then according to the general theory, you immediately have that this is a Lie group with a global parameterization. So you have to prove that this is actually a Lie group, but this is not easy. Okay, so this is easy. Okay, so this is easy. So you just need to prove that the operations are continuous, the group operations are continuous in this topology, and according to our intuition, the Lie bracket in this group is just the commutator of two operators. Okay? Because essentially it's more or less like the classical matrix Lie groups. Okay, what about the exponential map? Yeah, because we know that, of course, for every Lie algebra, the exponential map is extremely principal. It appears that this situation is very simple in this setting, and the reason is that if you take V, any element from V, in terms of action on the polynomial, it reduces the degree, okay, by one, at least by one. So which means that if I take any monomial of power n, by applying n times, I will make it zero. So which means that if I have infinite series, right, and I act of V to power n, and I acted on a monomial, or on any polynomial, then actually only a finite number of terms survive. So this means that the exponent is well defined by using this formula as an element of m, and at the same time, I can also construct the log of every monic polynomial sequence again, because by using this formula, right, the Taylor's formula for logarithm, p minus 1 reduces the degree of polynomial, again applied to every monomial, it will vanish starting from something. So what I really have, therefore, is the second way to parameterize my Morning group, and this is by using log of p. So before I had p minus 1. So this was one parameterization, and this is the second parameterization. So the space V is still the same, but I have two different parameterizations. Now I want to describe the Lie structures on the space on the Sheffer group, and in order to do this, I need to discuss a little bit about the differentiation of polynomials of infinite dimensional space. So assume that I have a function f defined on my Hilbert space H minus, and I choose any direction zeta from H minus. Then what I'm doing the directional derivative of S in direction zeta, which is called Gateau derivative. Right? I'm taking the increment f of omega plus t zeta, and I differentiate this in t at point 0. So this is the directional derivative. Now, if I apply such kind of differentiation, let's say to a monomial, right? So what I have here is a monomial, and let's say I differentiate k times. What I'm going to get? I will get, of course, the factor, the Pochhammer symbol nk, so n minus 1, n minus k plus 1. Then each time when I differentiate in direction zeta, I will actually get the pairing of zeta with omega, and this will be k times, right? Which I can write this way. Okay, and then there will be the remaining part of the monomial. Okay, so now given this operation, I will define the k's power of the gradient. So of course I should probably start with the first power of the gradient, but I will start with the k's power of the gradient. Yeah? So general k. So what happens? What is this gradient? So it is a map which is applied to polynomials. And as a result of this map, I get a polynomial O times element of the k's tensor power of the positive space. Okay, so to be more, this map is defined in such a way that if I take k's power of the directional derivative of in direction zeta, then this is just dual pairing of zeta to power k with the k's gradient of p of n. Okay, so this can be done, and explicitly, if you apply the k's gradient to the monomial, so what it does, it takes k elements out of the monomial. So the monomial is now reduced to the degree omega n minus k. Yes, dual pairing with cn minus k. And here on the left, of course, I have Pochhammer symbol and k, and I still have c to power k. So c to power k is now the element of this k's tensor power. Okay, so now I have this k's differentiation, and now as soon as I apply a linear operator to the result of this differentiation. So if I take a linear operator which maps the k's tensor power of h plus each of the say real numbers, okay, then I can look at this product, right? So the k's tensor power or the k's power of the gradient gives me an element of this space, and now I apply operator to this part, And this gives me a real number. And this gives me a real number. So therefore, altogether, this is nothing else but a linear continuous operator on this space of polynomial. So more explicitly, if you have such an expression and you apply it to a monomial, so what you get is this one here. So this expression is clear, and what you have here, you take C to K, a K applied to this vector gives me a real number, so it's fine. So this is one kind of operator that I will use. And the second kind of operator that I'll need in my considerations is when I now map BK. So BK now acts from the case tensor power to the first, just to the Hilbert space. Okay, so when I apply BK, right, when I apply BK from here, right, then this will be an element of H plus. So what I'll do with this element, I'll take the dual pairing of this element. I'll take the dual pairing of this element with omega. Omega is the variable. Omega is the variable. So essentially, you can treat this as multiplication by omega. So explicitly, what happens in this case, so if I have such an operator applied to a monomial, so I still have this factor nk, but now the difference was that before ak applied to ck was a number. Now this is an element of H plus, and I took dual pairing with omega. Okay, so if you think in terms of the, let's say on the real line, then what happens is that I first take the case derivative, and then I multiply by the variable. Because multiplication by the variable is a continuous linear operator on the space of polynomials. But anyway, the conclusion is that I have for any operators ak, which act from H plus to k, a linear, continuous linear operator on polynomials ak delta k, and similarly for each bk from here, I have this linear operator. Now that I have this, I'm actually able to give a full description of of the Lie group and Lie algebra of the Sheffer group. So the first statement is that Sheffer group, Appel group, and group of binomial sequences are all Lie subgroups of M. So this means in particular that they are closed, right? So I have this space V, right? Locally convex topological vector space, which gave me the description of the topology on the space of all monic polynomial sequences. The corresponding part, the part of the Lie algebra of S, A, and B are closed. And furthermore, I have explicit description of their Lie algebras. And this explicit description happens via the exponential maps. So the exponential maps are, of course, in the sense of, as we said before, in terms of taken powers of those operator valued matrices. Okay, so explicitly, the Lie algebra of the Sheffer group is the set of all operators V from Blackboard V for which the exponent is an S, for V A for which the exponent in A, and for B exponent in B. Okay, so this has been shown, but one can really show that first. These are really the Lie algebras of S, A, and B, right? It's just like in the classical theory of matrix Lie theory, where you have the statement that any matrix Lie group, Lie algebra of any matrix Lie group is exactly the can be represented through the exponential maps. But of course, not like this, sorry. And the main point is that I have this explicit description of these Lie algebras. So first, the Lie algebra of the upper group. So the Lie algebra of the upper group is exactly the algebra of all series of this form. Okay, so AK maps the case tensor power into R, okay, and delta K. Okay, again, no problems with infinite series because gradient reduces the degree of the polynomial. So which means that if you apply it to any polynomial, only a finite number of terms survive. So this was the Lie algebra of the upper group. The Lie algebra of the group of binomial sequences is given by all sequences of this form. So K now, so before K started from 1, now K starts from 2. Okay, so what I have K's power of the gradient, apply BK. BK is an arbitrary linear operator, and then take GL pairing with omega, multiply by n. And finally, S is just the linear span of these two. So which means that any element of the Lie algebra of the Sheffer group is a sum of this operator and sum of this operator. Okay, so this is already full description of the Lie algebra, but then the question is, what is exactly the form of the Lie bracket? So we said that from the point of view of the general theory, the Lie bracket of any V1 and V2 is nothing else but the commutator. So V1, V2 minus V2, V1. But given that, what is the form in terms of these operations? Okay, so what I'll need to do in order to achieve this, I will again use the language of the formal power series. So I'll take operators A, K, and BK like here, and I sort of replace gradient by variable from the space H plus, okay, tensor power. So I'm looking now at the formal tensor power series. I'm looking A of C as this formal tensor power series. Okay, whatever, it's just defined as a combinatorial object. And big C, right? C, K's power, big C, so this is an element of H plus. Now, if you look at these formulas, then of course you may say, okay, now let's interpret this. So if I have this representation, then I will write this as A of gradient, right? And here as omega B of gradient. Okay, so I interpret in this way elements of my Lie algebra. But now that I have a formal power series, I can actually differentiate this. Well, differentiation of a formal power series is a well-defined object, right? You just differentiate each term. And in particular in this setting, so I take any element phi from H plus, right? Because our series is defined on H plus, and I take the Gauss derivative in the direction phi, okay? So this gives me a new formal tensor power series. Okay? So, and similarly here, having done this kind of differentiation, I may now speak about, at least formally, about, let's say, d phi A of delta, A of number, d phi B of number, right? I can do this. But I'll do even more. I will now use as a direction another formal tensor power series. Okay, just like you think of it as you fix element of C and you differentiate in that direction. It's the vector field. Okay? So therefore, you can now treat this as this sort of direction. And now that we have this kind of preparation, we have complete description of the Lie brackets on the Lie algebra. So first A. So I recall that A is just the formal power series of the gradient. So this is the group A, the group upper group was commutative, treating the Lie bracket is 0. So this is no result. So still to be here. Now, what happens if I take two elements from the Lie algebra of the binomial group? And the statement is that their Lie bracket, equivalently their commutator, will be again an element of this form, right? Where what is written here? I take B1 formal power series, I differentiate it in the direction of B2 formal power series, I take this formal power series and I substitute gradient minus vice versa, right? Just it's very much, of course, similar to the usual procedure how you differentiate vector field. Yeah, so you do these differences and eventually, so you first do this at the formal level, but then you substitute into these formula gradients, and this gives you well-defined operator, And finally, the cross between the Lie algebras A and B, right? Because any element of S is a sum of an element of A plus plus an element from B. If I take A of delta, element of the Lie algebra A, and omega B delta, element of B, then the Lie bracket between A of delta and omega B delta is you do the formal power series A, you differentiate it in the direction B, you obtain this formal power series, and then you do the graph. Okay, so this is the result, and then if I have just 1 minute, maybe I'll just add the idea how one proves this. So of course, in order to prove these results, one has to go to the language of formal power series, and one has to use the result about the product. Just a second. About the product of two Sheffer sequences. So this is the result. So this is this result that actually, if you take, for example, product of two binomial sequences, then you obtain the composition. So essentially, you prove the existence of the exponential map on these formal power series, kind of similarly to what you do with diffeomorphism groups, right? And then after you have done this, you go back to the Sheffer, to the, let's say, binomial group, and similarly with the upper group. Okay, so this is it.
Thank you very much. That very beautiful picture. It mimics everything what we know in finite dimensional. Please, any questions, comments, remarks?
I would like to ask you. Sorry.
Yeah. Yes, please, time.
Yes. It's very interesting talk. Also, thank you very much for your interesting report. But I would like to ask you that we know that Hilbert spaces are very popular in
which spaces?
Hilbert spaces.
Hilbert spaces, yes.
Yes, very popular in mathematics and in physics. But usually in physics we have only usually Hilbert space. Why did you decide to consider so-called Sheffer polynomials? The combination of this Hilbert spaces, their multiplication, different.
Sheffer, generally speaking, in analysis on infinite dimensional spaces, so we have had quite many important examples of Sheffer polynomial sequences. So just to give you an idea, just the most important and the most trivial example of actually upper sequence is the sequence of Hermite polynomials, right? For example, by using Hermite polynomials, one does the chaos decomposition for infinite dimension for L2 with respect to infinite dimensional Gaussian measure. So not only, so there are various instances where the polynomials on infinite dimensional spaces appear in various. So somehow I would say that the most important for applications would be first orthogonal polynomial, Sheffer orthogonal polynomial sequences, right? And a lot of research in particular has been done in particular in Kiev in this direction. Okay, and it was started actually by Yuri Makarovich Berezhansky. And furthermore, another important example of a Sheffer sequence, which is not orthogonal, are the so-called Fourier factorials. Again, Fourier factorials on an infinite dimensional space play a major role in the theory of point processes, for example.
And this space is normalized as Hilbert space.
Not necessarily. So if you take Hermite polynomials, well, they can be on a negative Hilbert space, or you may take them on a Schwarz space of temporal distributions, right? And as for Fourier factorials, you would probably take SH plus, let's say, this space of all continuous functions with complex support, and then analog of H minus wouldn't be Hilbert space. H minus would be the space of sine-Radon measures. But as I said, in principle, the theory that I discussed today works on some set of infinite dimensional Hilbert spaces, and I just chose Hilbert space because the language is the easiest. Let's say even if you replace Hilbert space with a Banach space, one uses already additional time to explain what is the tensor product of Banach spaces, because it's not kind of unique. With Hilbert spaces, it's sort of unique because there is a unique tensor product of Hilbert spaces, which gives you a tensor space, Hilbert space. If you take Banach spaces, there are various possibilities to make them Banach spaces.
Thank you.
Thank you very much.
Can I ask?
Yes, maybe a very short question, because we have another now.
Yes, I understand. Can it be cases of your group S, which is semi-direct product A and B, in which this group S is Frobenius group, namely A in your case is abelian group, and it's kernel of Frobenius group, and group B have to have even order. In this case, your group can be a Frobenius group, but it have to fix one point.
I don't know. So instances. No, it's, to be honest, abelian group, yes, with respect. Even if you take
it can be some case of a Frobenius group. Maybe your semi-direct product satisfy condition.
Yeah, I would say the best question. I don't know the answer to your question, but I would say the first thing to check would be whether this is true when you have just polynomials in the real line. Just your Hilbert spaces are. So I don't know whether this group would have this property.
Okay.
We can classify it if we ask a question, does your complement group B fix one point?
No, here maybe Frobenius groups are related with finite groups. Yes, finite permutations groups, and now this in finite dimensional space. So this is another.
I thought not only finite, but maybe.
What I would like to say that if you Google Riordan group, there is actually a huge volume of algebraic papers related, and this is equivalent. This is equivalent. Sure. So maybe they study somewhere. I haven't seen, but I wouldn't claim that such a result does not exist, to be honest.
Yes, and group or upper triangle matrix, could it be subgroup of Borel subgroup? It's upper triangle, but with determinant not one. I saw.
But the determinant here makes no sense because this is infinite matrix. By the way, a Riordan group will be lower triangle. It's equivalent. But
in one case, I saw upper triangle group.
Yeah, in my case, it was upper triangular, but when you look at the algebraic papers, they would be dealing with a lower triangle, but it's the same. But the determinant is not defined because it's infinite matrix, so you can't define it.
Okay. Thank you.
Okay, so thank you very much. Thank you very much. Very, very interesting talk and very interesting picture which you draw here. Very beautiful.